A 4 metric ton truck traveling at 90 km per hour collides with a stationary 1 metric ton car. If the vehicles remain joined together, what is their velocity immediately after collision? What percentage of the kinetic energy is lost as a result of the collision? Okay, this is not different from the situations we discussed so far. Now, we have a 4 metric ton truck traveling to the right at 90 km per hour. Convert that to meter per second. It is 25 meters per second. And it is going to collide with a poor car right there. And the two joins together and moves forward. That is the situation. So mass of the truck M1 is 4,000 kilograms. Its initial velocity before collision V1I is 90 km per hour. That is 25 meters per second. Therefore, its momentum before collision P1I, look at that, initial momentum of the first object, P1I, is its mass times the initial velocity, and that is 10 to the power 5 kilogram meter per second. Okay? The mass of the car is M2, that is 1,000 kilogram, 1 metric ton. A metric ton is 1,000 kilogram. So 1 metric ton is 1,000 kilogram. And before collision, the car is at rest. V2I equal to 0. Therefore, what is the initial momentum of the car? What is the momentum of the car before collision? P2I equal to 0. So what is the total momentum of the car truck system before collision? Pi. Initial momentum of the system is P1I plus P2I. That is, P1I is 10 to the power 5 kilogram meter per second. P2I is 0, therefore the total initial momentum is 10 to the power 5 kilogram meter per second. Alright? We need to find the velocity of the system after they collide. They collide, joins together, and let's assume that the combined velocity of the wreck after they collide is V sub f. Let Vf be the velocity of the combined system after collision. Then the combined, what will be the combined mass after collision? The mass of the truck is 4 metric ton. The mass of the car is 1 metric ton. The total mass is 5 metric ton. That is 5,000 kilograms. So what is the momentum of the system? That means the truck and the car joined together. It will be 5,000 kilogram times Vf. That will be the final momentum. Let's write that down. So Pf, the final momentum, is 5,000 Vf kilogram meter per second. We know the initial momentum of the system. We now know the final momentum of the system. Apply the conservation of momentum. Pi must be equal to Pf. Therefore, 10 to the power 5 kilogram meter per second equal to 5,000 kilogram times Vf. Can we solve for Vf? Yes. Vf is 10 to the power 5 divided by 5,000. That is 20 meter per second. After the truck collides with the car, they join together and move in the direction in which the truck was coming. That's why the final velocity is positive. Okay. B. What is B part? In the process of collision, some kinetic energy is lost. We need to find the percentage of kinetic energy lost. Alright, what is the total kinetic energy of the truck and the car before collision? Kinetic energy is 1/2 mv squared. So Ki, initial kinetic energy, is the initial kinetic energy of the truck plus the initial kinetic energy of the car. Well, we know the mass of the truck, we know the initial velocity of the truck. Do you remember that value? Initial velocity of the truck? 25 meters per second. Tell me, what is the initial kinetic energy of the car? The car initially was at rest. Its initial kinetic energy is 0. Alright, so this is now 1/2 m mass of the truck times its velocity squared. This is the initial kinetic energy of the truck plus the initial kinetic energy of the car is 0. And that gives me Ki equal to 1.25 times 10 to the 6 joules. Now I urge you, when you watch these lectures, always be ready with calculator, paper and pencil. Work these out with me. Be very active in learning. Alright, so the initial kinetic energy is 1.25 times 10 to the 6 joules. What is the final kinetic energy? After collision, they join together so that their total mass is m1 plus m2, and that is 5,000 kilogram, and the common velocity is Vf. So the final kinetic energy is 1/2 m1 plus m2 Vf squared, and that will be 1/2 of 5,000 times, we calculated Vf as 20 meters per second, and that is 10 to the power of 6 joules. Alright, what is the kinetic energy lost? Kinetic energy lost is initial energy minus the final energy. Is that right? That's the amount lost. That is 1.25 times 10 to the 6 minus 10 to the 6. Can you put that in your calculator and give me a value? Is this right? 250,000 joules. In the process of collision, we say the kinetic energy lost is 250,000 joules. Now tell me, is this consistent with the conservation of energy? Can energy be lost? Well, one form of energy can be lost, but that should appear in other forms of energy. But total energy cannot be lost. Kinetic energy can be lost. Now tell me, what happened to this lost kinetic energy? The truck comes and hits on the car, and in the process of that hitting, there is a loss of kinetic energy of 250,000 joules. What happened to this lost kinetic energy? Can you think about it? Well, some part of that is used in doing work on the car. Is that right? The car has been made into half its value, or half its length. Is that right? The car has been squished up. The energy needed to do that work come from this lost kinetic energy. And there is a lot of sound, vibrations, and many other forms of energy. So this lost kinetic energy is not simply lost, it's being converted to other forms of energy. What is the percentage of kinetic energy lost? Now, how do you write the lost percentage? Now, it will be the amount lost divided by the original value multiplied by 100. That's how you calculate the percentage lost. The amount of energy lost divided by the original amount multiplied by 100. Look at that. Ki minus Kf over Ki multiplied by 100. That will be the percentage of energy lost. That is 250,000 divided by 1.25 times 10 to the 6 multiplied by 100, and calculate that for me. I got it as 20%. 20% of the original kinetic energy of the truck has been lost in doing work against that, well, in doing work on the car. Also work is done on the truck itself. The bumper of the truck is definitely bent. Where does that energy come from? It takes an enormous amount of energy to bend those things. And all that comes from this amount of kinetic energy. Okay, let's now look at another problem. An isolated 3 kilogram object initially at rest explodes and splits into 3 fragments. One fragment has a mass of 0.5 kilogram and flies off along the negative x-axis at a speed of 2.8 meters per second. And another has a mass of 1.3 kilogram and flies off along the negative y-axis at a speed of 1.5 meters per second. What is the speed and direction of the third fragment? Well, this is the same as you keep a nut on a table and hit it with a hammer. What happens? The nut will break and the pieces will fly off in all directions. Why do the pieces fly off in all directions? Well, to conserve momentum. The law of conservation of momentum. What is the momentum of the nut before you crack it? 0. That means after you crack it, if you add the momentum of all the pieces, it must be equal to 0. That means if one piece flies off in the positive direction, another piece flies off in the negative direction, the total momentum there will be 0. Well, this is the situation here. We have an object that explodes. And I have actually put those 3 pieces there. It explodes into 3 pieces. What is the total momentum of the object before exploding? 0. That means the total momentum of the 3 pieces, when you add, must be equal to 0. That is the principle we are going to use in solving this problem. Okay. Total momentum of the object before explosion, PI equal to 0. Well, it's going to explode now. Watch what happens to the first piece. One fragment that has a mass 0.5 kilogram moves to the right. So it goes to the right with a speed of negative 2.8 meters per second I. Why negative? In the negative x direction. And we know its mass. Its mass is 0.5 kilogram. The second piece goes in the negative x direction with a speed of 1.5 meter per second. So the velocity of the second piece is negative 1.5 meter per second J. Now watch how we represent the x and y directions. It's very important to do that. And now what happens to the third piece? The third piece must go somewhere in that direction so that the total momentum remains 0. We need to find the final velocity of the third piece, and I call it V3F. So V1F is negative 2.8 meter per second I. V2F is negative 1.5 meter per second J. We need to find V3F. Alright, let's set it up. Mass of the first fragment is 0.5 kilogram. Its velocity after the explosion is negative 2.8 meter per second I. Therefore, what is its momentum after the explosion? Let's call it P1F, final momentum of the first object. Its mass multiplied by its velocity. What's the direction? It's very important. That will be negative 1.4 kilogram meter per second I. This is the momentum of the first fragment after explosion. Let's now take the second fragment. The mass of the second fragment is 1.3 kilogram. Its velocity after explosion is negative 1.5 meter per second J. Therefore, P2F, the final momentum of the second object, its mass times its velocity, and that is negative 1.95 kilogram meter per second J. What is the mass of the third fragment? The total mass before explosion is 3 kilogram. Out of that, the mass of the first kilogram is the mass of the first fragment is 0.5 kilogram. The mass of the second fragment is 1.3 kilogram. Therefore, the mass of the remaining must be 3 minus the sum of the masses of the first two pieces. That will be 1.2 kilogram. So, the mass of the third fragment is 1.2 kilogram and its velocity is v3f. Let's go to the other slide. And I have brought all these important values with me. Final momentum of the first fragment, final momentum of the second fragment, and the mass of the third piece. Well, what is wrong in here? The mass is not a vector quantity, so just take away that J. That J does not belong there. Okay, let the velocity of the third fragment v3f, remember v3f is the velocity that makes an angle with the x-axis. So let's say its x component is x and its y component is y. So let v3f be xi plus yj. I hope you understood what this is about. If you remember, this is the v3f that we have drawn. Its x component, we are simply going to call it x. And the y component, we are going to call it y. We need to find these x and y. So let the velocity of the third fragment in the component form be v3f equal to xi plus yj. Then its momentum will be P3f equal to 1.2 kilogram mass times velocity. Velocity is xi plus yj. Now, what is therefore the total momentum of the three fragments after explosion? It will be P1f plus P2f plus P3f. This is P1f, negative 1.4. This is P2f, negative 1.95. Plus, this is P3f, mass of the third fragment, times its velocity in the component form. That means the momentum of that third piece has an x component and a y component. What is the x component of this momentum? It will be 12xi. And the x component, the y component of this momentum is 12yj. Alright. So, Pf, let's combine the i's and the j's. Look at this. The final momentum can now be written as the final momentum of the third fragment in the x direction is 12xi. And the final momentum of the first object is negative 1.4i. We can add the momenta in the x direction. It will be 1.2x minus 1.4i. That is the x momentum of the three fragments after explosion. And what is the y momentum of the three fragments after explosion? The y momentum of the third fragment is 1.2 yj, and the momentum of the second object is negative 1.95 j. Add those two together, that will give me the y momentum of the three fragments after explosion. That would be 1.2 y minus 1.95 j. This is the most important step here. The final momentum in the component form. We added the x components of all this and then the y components to obtain this. Well, using the conservation of momentum, you know that Pf equal to Pi, and Pi, the initial momentum, is 0. Therefore, the final momentum also must be 0. Well, if the final momentum is 0, it means the x component of the final momentum is 0 and the y component of the final momentum is 0. Is that right? They separately has to be 0 if the final momentum is 0. So we first take the x component and set it equal to 0. 1.2x minus 1.4 equal to 0. Solving that for x gives me x equal to 1.17 meter per second. What does x represent? X represents the x component of the velocity of the third fragment. We are looking for V3F, this V3F. And this 1.17 is the x component of that velocity. Similarly, take the y component of the final momentum and set it equal to 0. And that gives me y equal to 1.63 meter per second. So what is V3F now in the component form? V3F is xi plus yj. We have solved for x and y. It's equal to 1.17 meter per second I, that is the x value, plus 1.63 meter per second j. And we can now find the magnitude and angle of that velocity. You know how to do that. The magnitude of V3F is square root of x squared plus y squared. And that is 20 meter per second. And what is the angle? How do you find the angle? Theta equal to tan inverse of y divided by x. Theta is tan inverse of y is 1.63, x is 1.17. And that is 54 degrees. That means after the explosion, the third piece will move with a velocity of 20 meters per second at an angle 54 degrees, so that the total momentum of the three pieces after collision is 0. Isn't this a beautiful problem? I think so. Well, I want you to go through this and learn the technique of this problem one more time. Okay? Let's look at another problem. A 16-gram bullet is fired into the bob of a pendulum of mass 1.5 kilogram. When the bob is at its maximum height, the string makes an angle 60 degrees with the vertical. If the length of the pendulum is 2.3 meter, find the speed of the bullet. Well, here we can actually use the conservation of energy and conservation of momentum, and that is the way we're going to solve this problem. Now let me show you what this problem is talking about. You have a small ball of 16 gram, is that right? A 16-gram ball is fired into a 1.5 kilogram pendulum. This is the pendulum. It can move, is that right? It can swing. Okay. Now what I'm going to do is I'm going to charge my gun and I'm going to fire this ball into the pendulum and see what happens. There you are. The pendulum swung and now it makes an angle of 60 degrees with the vertical. You are given the length of the pendulum. What we need to figure out is the initial velocity with which this ball was fired. Now, if you notice, when the ball is fired, it has a velocity. That means there is an initial momentum, and with that momentum there is a collision. Now, after the collision, the pendulum and the ball move away together. The momentum is conserved. The total momentum before collision equal to total momentum after collision. So we can now use the conservation of momentum here, and also once the ball hits the pendulum, the two together has a velocity, has a speed. That means this pendulum ball system will have a kinetic energy, and that kinetic energy is going to become potential energy when the pendulum climbs to a height. Now we're going to use the conservation of energy there. What's there? Well, it didn't work, did it? The pendulum refused to get stuck there. Let me try it again. There you are. The initial kinetic energy of the system became potential energy of the system. Alright, this is what we're going to use in solving this problem. Well, I have done a very poor drawing here. This is the pendulum of mass 1.5 kilogram and length 2.3 meter. We don't know the velocity of the bullet on impact. Let that velocity be v. There it comes and impacts. Now, mass of the bullet is 16 gram, that is 0.016 kilogram. Therefore, its initial momentum, P1I, initial momentum of the first object, that is the bullet, is its mass times its velocity, 0.016 v kilogram meter per second. Now the bob initially is at rest. The pendulum is initially at rest. Therefore, its momentum initially is 0. The total momentum Pi is momentum of the ball plus the momentum of the pendulum bob, which is this quantity plus 0. That is 0.016 v kilogram meter per second. After the bullet hits the bob, they become a single system of total mass 1.5 kilogram plus 0.016 kilogram mass of the pendulum plus the mass of the little ball, and that is 1.516 kilogram, and moves away with a speed of Vf, a velocity Vf, so that the final momentum Pf is 1.516 Vf, and that Pf must be equal to Pi. Is that right? Now this is the Vf, the final velocity. Pf equal to Pi gives you this relation, 1.516 Vf equal to 0.016 v. Now we cannot solve anything from there because there are two quantities we don't know. So using the conservation of momentum, we got one equation. We will now go and use the conservation of energy to produce another equation. Let's do that. So this is the first equation, 1.516 Vf equal to 0.016 v. We can now find the Vf, the common velocity of the bob and the bullet, by using the conservation of energy. The kinetic energy of the bob and the bullet together immediately after the impact. You see, Vf is the velocity, the common velocity of the bullet and the pendulum bob immediately after impact. Therefore, its kinetic energy will be 1/2 m1 plus m2 Vf squared. And we know m1 plus m2, we don't know Vf. And that will be 1/2 times 1.516 Vf squared. This is the kinetic energy of the system immediately after impact. And that is 0.755 Vf squared. What happens after impact? With this kinetic energy, the bob climbs to a height h so that the string makes an angle 60 degrees with the initial position, as I demonstrated that to you. So this is now going to go and rise so that the string now makes an angle 60 degrees. There you are. And if this is O and this point is A, then in the triangle OAB, the length OB, which is the length of the pendulum, is given to be 2.3 meter. That's 2.3 meter. Now, therefore, we can find the length OA. You see, if this is 60 degrees, OA is the adjacent side and 2.3 is the hypotenuse. Therefore, OA divided by 2.3 is cos 60 degrees, and that gives us OA equal to 2.3 cos 60 degrees. That is 1.15 meter. Now, if this OA is 1.15 meter and the whole length of the pendulum is 2.3 meter, what is this distance? So this distance OA is 1.15 meter. Therefore, what is that distance? That is the height to which the pendulum has been raised, isn't it? When the pendulum is hit, it rises, and this is the vertical height h, and that h equal to the whole length is 2.3, the length of the pendulum. OA is 1.15. Therefore, that h is 2.3 minus 1.15. That is 1.15 meter. So the system has been raised to that height. What is the potential energy of the system? The potential energy of the system is the total mass m1 plus m2 times g times h, and that is 1.516 kilogram is the total mass, times g times h, the height to which the system rises is 1.15 meter. That is 17.1 joules. And this potential energy must be equal to this kinetic energy according to the law of conservation of energy. So using conservation of energy, you have the kinetic energy must be equal to potential energy. 0.755 Vf squared is 17.1. That gives me Vf equal to square root of 17.1 over 0.755. That is 4.8 meter per second. That is the velocity of, as soon as the bullet hits the pendulum and the bullet together move away with this velocity. Alright, let's now go back to our first equation. Which is our first equation? We have 1.516 Vf equal to, this is the first equation we have, 1.516 Vf equal to 0.016 V. That is the first equation we obtained using the conservation of momentum. Now we use the conservation of energy and obtain the value of that Vf. Using that, we can now find the V. V equal to 1.516 Vf divided by 0.016. and that is using the value of Vf. We get that is 455 meter per second, and that is the velocity of impact of the bullet. Let's do one more problem. To get off a frozen frictionless lake, a 70 kilogram person takes off a 0.15 kilogram shoe and throws it horizontally directly away from the shore with a speed of 2 meters per second. If the person is 5 meters from the shore, how long will it take for him to reach it? You see, a very interesting situation. A person is stranded in the middle of a lake and he has no way of, the ice is completely frictionless. So what is he doing? He's taking a pair of shoes and throwing it in the opposite direction where he wants to go, so that the initial momentum is forward, then you will get a momentum backward, alright, so that you can get off the lake. That is what the person is doing. Alright, the system here consists of the man and the shoes. The action here is throwing the shoe. Before the action, both the man and the shoe are at rest. So what is the total momentum before that action? The initial momentum before action is 0. The momentum of the shoe after the action is 0.15 kilogram times 2 meters per second. That will be 0.3 kilogram meter per second. Alright. If V is the velocity of the man after action, then what will be his momentum after the action? It will be his mass times his velocity. So the action is throwing the shoes, and after the action his momentum will be backward. That will be 70 V kilogram meter per second. So PF is 0.3 plus 70 V. 0.3 is the momentum of the shoe, and 70 V is the momentum of the man. So the total momentum after the action, after throwing, is this. What is the total initial momentum? 0. Therefore, initial momentum must be equal to the final momentum. That means this quantity must be 0. We have 0.3 plus 70 V equal to 0, and what does that give you? We get the velocity of the man, a pathetically low value, negative 4.3 times 10 to the negative 3 meter per second. What does the negative sign tell you? That the velocity of the man is opposite to the velocity of the shoe. Alright, if he has to travel a distance of 5 meters with this pathetic velocity, how long will it take? Well, if t is the time taken, that t will be the distance he needs to travel divided by his speed of motion, and that is 1.16 times 10 to the 3 seconds. An awful lot of time he is going to get frozen to death. I wish he could throw that shoe a little faster. Or maybe next time you go to such places, buy great big heavy shoes so that you can throw at a tremendously big speed. We will solve one more problem before we close this lesson. A 1600 kilogram empty hopper car rolls under a loading bin with a speed of 2.5 meters per second, and a 3,500 kilogram load is deposited in the car. What is the velocity of the car immediately after being loaded? Now, do you see any connection between this problem and the first situation of the little trolley and the brick deposited on it? Isn't this exactly the same? Now, if you go into a coal mine, you will see this situation very often. The hopper car will roll in, the coal will be deposited in it, and the hopper car will move away. Now, conservation of momentum is very important in situations like this. The momentum of the hopper car before loading is its mass times its velocity. 1600 kilogram times 2.5 meter per second, that is 4000 kilogram meter per second. So the hopper car moves in, this is where the hopper car comes in, and the load gets deposited on it at that time and it moves away. The total momentum before the loading, the action here is the loading. So the total momentum before loading must be equal to the total momentum after loading. Okay? The momentum of the load before loading is 0. Is that right? The load is at rest before it being put in the hopper car. So the momentum of the load before it gets loaded is 0. So what is the total momentum before the action of loading? The total momentum will be 4000 kilogram meter per second plus 0, which is 4000 kilogram meter per second. And once loaded, the hopper car and the load together is a single system. And what is the total mass? The mass of the hopper car is 1600 kilogram. Mass of the load is 3500 kilogram. The total mass of the system now is 5100 kilogram. And that 5100 kilogram is now going to move with the velocity which we need to calculate. Let that velocity be v meter per second. Therefore, what is the momentum of the car and the load after loading? It will be the total mass multiplied by that common velocity after loaded. So PF is 5100 kilogram times v meter per second. That is 5100 v kilogram meter per second. Now, this total momentum of the combined system must be equal to the total momentum of the system before loading. So we have PF equal to PI, 4000 kilogram meter per second equal to 5100 V kilogram meter per second. Therefore, what is this V? V is therefore 0.78 meter per second. After loading, the hopper car and the load will move away with a speed of 0.78 meter per second. You can see conservation of momentum and conservation of energy are used all around us. And these properties are very important. In fact, the universe, the law that governs the universe is actually held in place with these two very important principles. The conservation of energy and the conservation of momentum are the most important properties that govern the way the universe functions. All right, I'm going to stop this lesson here. I will get back to you with lesson 4 later on.